The last part of section 3.9 is a technique called logarithmic differentiation. And this is going to allow us to use the properties of logs to break apart a really complicated expression into easier pieces, so that we can differentiate the pieces one at a time. But the problem isn't going to start off with logs in it. We're going to put the log in it at the beginning so that we can use those properties of logs. We just have to remember at the end to take it back out. So we had said earlier that we had all these properties of logs that if we could remember them from algebra class, they're going to make a whole bunch of these problems easier. If we see multiplication inside of the log, we can separate it with addition. If we see division inside of the log, we can separate it with subtraction. And if we see something inside a log that has a power, the power can come out front as a coefficient. And the right-hand side of these equations are a lot easier to find derivatives for because with addition and subtraction, we can take the derivative of those pieces individually, where on the left-hand side, we would have to do like chain rule and product rule and quotient rule. And that last one, number 3, we would have to do like a double chain rule, where the right-hand side, b is just a coefficient now, and it's going to transfer to the answer. So we want to introduce a log into these expressions so that we can use those properties and simplify them tremendously and make these derivatives a whole lot easier. The problem is they don't start off with logs. So the goal here is going to be to introduce a logarithm into a problem, a derivative problem, so that we can utilize all of those properties. That allow us to break apart that really complicated expression into much simpler pieces. And those pieces are much easier to find the derivatives for. So obviously you can read this, but we want to introduce a logarithm into a derivative problem so that we can utilize all of those log properties that allow us to break apart a complicated expression into pieces that are much easier to differentiate. So let me show you how we're going to do this. We're going to be asked to find the derivative of something really complicated that's got product rule, quotient rule, and chain rule. And we saw some a few sections ago where we had to use multiple properties, but these are going to be even crazier. So we might have, let's say, x cubed minus 2 to the 5th times 3x minus 1 to the 7th all over the square root of 5x minus 9. We want the derivative of that. So it's going to start off, if we did this, without logarithms. It's going to start off as a quotient rule. And in the process of doing the quotient rule, the top we would have to do the chain rule, or excuse me, the product rule. And then while we're doing the product rule, the individual pieces would require the chain rule. In the process of doing the derivative of the bottom, we'd do the chain rule. It's a lot of work. And we'd have to do product rule, quotient rule, and chain rule on all three pieces. So it is a lot of work. But if we could throw a logarithm in front of this is going to separate out into three separate pieces whose derivatives are much, much simpler. So what we're going to do here is we're going to throw a log in front. And yes, we are allowed to do that as long as we remember that we did it. So the way that I like to remember that I did that is I set this equal to y. So I'm going to say y equals x cubed minus 2 to the 5th times 3x minus 1 to the 7th all over the square root of 5x minus 9. That's what we're trying to find the derivative for. And I'm allowed to throw a log in front of it as long as I do the exact same thing to the other side. It's mathematically, it is legal as long as we do it to both sides of the equation. So now on the right-hand side, we can use our properties of logs to separate that out into all sorts of individual terms, because the individual terms are much easier to differentiate. So the natural log of y is going to equal, well, the two pieces in the top are being multiplied, so we can separate them with addition. So it's going to be the natural log of x cubed minus 2 to the 5th plus the natural log of 3x minus 1 to the 7th. And then we've got a denominator, so that's going to be subtraction, natural log of the square root of 5x minus 9. So now when we do derivative, it's three separate derivatives, and there is no more product rule or quotient rule. There's no more multiplication and division, but there's one more property of logs that we can use that's now going to avoid chain rule, because that third property of logs says if we're taking something, the log of something that has a power, the power can come out front as a coefficient. So we can really simplify this even further and say this is 5 times the natural log of x cubed minus 2 plus 7 times the natural log of 3x minus 1. Minus, and remember, square root is a 1/2 power, so this is 1/2 natural log of 5x minus 9. And now the derivative is going to be even easier. So our goal was to find the derivative of this. So I'm going to go through and take the derivative. So now the trick is we also have to take the derivative of the left-hand side, which has a y, so it's like an implicit derivative. So that's what the catch is here, is that we've got that y in there, and we're doing the derivative with respect to x, so it's like an implicit derivative. So anytime we're doing the derivative of a log, whatever is inside goes in the bottom, and its derivative goes in the top. So this is 1 over y. But also anytime you do the derivative of a y, you've got to attach a dy dx. So 1 over y dy dx for the left. On the right, everything has x's in it. So we can just do our normal log derivatives. So the derivative for a log, whatever's inside, goes in the bottom of the fraction. And then my 5 just carries along to my answer. And then the derivative of the inside goes in the numerator. So I'm going to put 3x squared in the top. And then plus, and then same thing for the next term. Whatever is inside the log goes in the denominator. 7 carries along to the answer. Coefficient just carries along to the answer. The derivative of what's inside goes in the numerator. And then subtraction. And then I've got 1/2 Whatever is inside the log goes in the denominator, its derivative goes in the numerator. Now our goal here, if I say the original was equal to y, then our goal is to find dy dx. And we almost have that. What we have is 1 over y dy dx. So all we have to do is just get rid of that 1 over y, and I can get rid of that if I just multiply both sides by y. And multiplying both sides by y is really just multiplying both sides by the original expression. So we just need to clean this up a little bit and multiply by the original expression. So dy dx equals 15x squared over x cubed minus 2 plus 21 over 3x minus 1 minus 5 over 2 times 5x minus 9. You could multiply that out if you want. All times y, because I just want to know what dy dx is. That's the derivative. Our goal initially was to find the derivative, which is dy dx. So y, we said, was equal to the original expression. Y was x cubed minus 2 to the 5th and then 3x minus 1 to the 7th all over square root of 5x minus 9. That is our derivative. And we don't need to waste a whole lot of time trying to do some algebra simplification. I'm sure there's something that we could do to simplify that. We're happy with this. Okay, so just to recap a little bit. We're given some really complicated derivative to find. It involves a whole bunch of products and quotients and powers. What we're going to do is we're going to put a log in the front of it. And that's going to allow us to break it up into individual terms and pull the exponents out as coefficients. And then we can just take the derivative of those individual logs. The trade-off for this is that it's an implicit derivative because we also have to take the derivative of the left-hand side, which is a natural log of y. So what we've really found is not dy dx. What we have found is 1 over y dy dx. So these three terms here are not our final answer. We actually have to multiply that y over. So those three fractions multiplied by the original y, multiplied by the original fraction, the original complicated expression is equal to our derivative. So we will look at another one. Let's find the derivative for the cubed root of x squared minus 5x over x to the 5th plus 9x squared cubed. So this would involve quotient rule and chain rule on both pieces, which we could work all of that out. It would maybe take almost a full sheet of paper depending on how large or small we write, how much detail and steps we write out. What we're going to do instead is we're going to try to do it with logs. So I'm going to say that this is equal to y, and I do that just so I can keep track of the log and not forget to multiply, forget that it's an implicit derivative and multiply that y over at the end. So I say y equals, and I'm going to leave a little bit of space because I'm going to throw a log in front in just a second, the cubed root of x squared minus 5x over x to the 5th plus 9x squared cubed. So I set my original expression equal to y, and I'm going to throw a log in front of both of them. As long as I do it to both sides, it's okay. And now I'm going to find the derivative of everything. So on the left-hand side, the derivative for natural log of y is 1 over y dy dx, because that's an implicit derivative. Oh, I need to use my properties of logs first. Hold on a second. I don't want to do my derivative yet. I'm getting ahead of myself. Let's go ahead and break up our right-hand side. We want to break up our right-hand side. So properties of logs say we can break up division with subtraction. So I'm going to do the natural log of my numerator minus the natural log of my denominator. And then we will bring those exponents out as coefficients. So a cubed root is the same as a 1/3 exponent, and it can come out front as a coefficient. And then that's got a cubed power. It'll come out front as a 3 coefficient. And now we are ready to take the derivative. Now we've got it separated out into individual terms, and the derivative will be a whole lot easier. There we go. Now the derivative for natural log of y is 1 over y dy dx. And these individual log derivatives, well, we've got our coefficient that just carries to the answer. And anytime you do a log derivative, you take what is inside of the log and you put it into a denominator. And then you take its derivative and you put it into the numerator. That's the rule for log. Anytime you take the derivative for a log, you just take what's inside and you put it into a denominator. And then you take its derivative and you put it into the numerator. And then we've got a completely different term, so we don't need any special rules. We just transfer down the subtraction. It is another log, so that tells me to start a fraction. Whatever is inside of the log goes in the denominator. Oops, that's a square. My 3 is just going to transfer down. It's a coefficient. And then whatever the derivative of that denominator is going to go in my numerator. We are trying to find dy dx. What I have right now is 1 over y dy dx. So to get rid of that 1 over y, I will multiply both sides by y. But y was the original expression, the red stuff. So our final answer here is 2x minus 5 over 3 times x squared minus 5x minus 3 times 5x to the 4th plus 18x over x to the 5th plus 9x squared. That's what we got from the derivative. Times our y, and the y was the original expression. The original expression is cubed root of x squared minus 5x over x to the 5th plus 9x squared cubed. So you'll always be, after you found the derivative for your logs, you'll always be multiplying by the original expression. That is always part of logarithmic differentiation. This whole idea of logarithmic differentiation is not absolutely necessary. It's just an option if you have this really, really crazy derivative that you're asked to find. And it's got lots of products and quotients and chains in it. logs, those properties of logs just allow us to break those apart into much easier derivatives. So if you recognize something that if there were a log in front, it would break down so much nicer and it would be so much easier to do the derivatives if there was a log in front, then you could use this method. You're not required to use this method, but you could. If this makes sense to you and you understand it, you certainly could throw a log in the front and use your properties of logs to break it apart. But we also could just do our quotient rule and then do our chain rule individually on each piece. Your final answer will look a little bit different just because it will have some different algebra simplification done to it, but it will be an equivalent answer. So the logarithmic differentiation is not absolutely necessary. It's just an option. It makes the derivatives easier. I personally think it makes the derivatives easier. And it's good to have some options. It's always good to have some options. Think outside the box. Apply some things that we've learned previously to help us make our life a little bit easier here now.